Here's something you've seen 100 times and probably never questioned. The night before an election, a poll comes out. Support is 47% plus or minus 3. And we all just nod. But think about it. Nobody called every voter in the country. They asked maybe 1,000 people. So where does that tidy little plus or minus 3 come from?
Right, and that's the whole game this week. You've got some true number out in the world you can't see directly, the real level of support, the true average of something, and all you have is a sample. The 47% is your best single guess. The plus or minus 3 is you being honest about how far off that guess might be.
So this is week 4, lecture 14, estimation and confidence intervals. By the end, that plus or minus won't be magic. It'll be something you compute. Let's get into it. So Jordan, frame this for me. How is this week different from everything we just did?
Good question. All of week 3 was probability. We knew the population, we knew mu, we knew sigma, and we asked how a random sample would behave. The truth was given. The sample was the unknown. This week, we flipped the arrow completely. Now the sample is what we have in hand, and the population mean, mu, is the mystery. We reason backward from the data we can see to the truth we can't. That's inference.
And the bridge between the two directions is exactly the sampling distributions we built last week, the Central Limit Theorem especially. That's what makes the backward trip possible. And that poll on the news? Perfect example. 47% plus or minus 3. The 47 is the estimate from the sample. The plus or minus 3 owns up to the guesswork. Same idea whether we're estimating a percentage or an average.
Let's start with the single best guess. If you want one number to stand in for the population mean mu, what do you use?
The sample mean, x bar. Add up your measurements, divide by how many you have. That's the point estimate of mu.
And we trust it for a concrete reason. The law of large numbers says x bar marches toward mu as the sample grows. So for a decent-sized sample, x bar lands close to the truth.
There's a nice property hiding here too. X bar is unbiased. The expected value of x bar is exactly mu. Averaged over all the samples you could have drawn, it sits right on the target. No systematic lean one way or the other.
Which is why we say x bar estimates mu. It's close with high probability, rather than just approximates it. The word matters.
But here's my problem with a single number. If I report x bar and walk away, I'm pretending I nailed it, and a different sample would have handed me a slightly different x bar.
Exactly the weakness. The point estimate is honest as far as it goes, but it's silent about how far off it might be. And it's almost surely not exactly mu. So instead, we report a range, x bar plus or minus a margin. That interval carries the guess and its uncertainty in one shot. It's the plus or minus 3 on the poll.
That range is the confidence interval. The rest of today is really one question. How big is that margin? Let's build it.
Before the formula, the idea, because almost everybody gets this one backward. When we say 95% confident, the thing that's random is not mu.
Wait, say more. What is random then?
Mu is a fixed number, unknown but fixed. It's not jiggling around. What moves is the interval. Every new sample gives a new x bar, and so a new interval.
So picture it on the right. Draw 20 samples, build an interval from each one. They scatter around the true mu, that dashed line. And the claim is that about 95% of those intervals actually cover mu.
Look at the picture. 19 of the 20 cross the line, and one misses entirely. Any single interval either covers mu or it doesn't. The 95% is the long-run hit rate of the procedure, not a probability about that one interval.
Okay, I'm sold on the idea. Where does the actual formula come from?
Straight from the Central Limit Theorem. It tells us that x bar minus mu over sigma over root m behaves like a standard normal z. So the chance that quantity lands between minus c alpha over 2 and plus c alpha over 2 is 1 minus alpha.
And then it's just algebra. You take that inequality and solve it for mu instead of for z.
Right. Shuffle the terms, and the statement about z turns into a statement about mu sitting in a window around x bar. And out pops the headline formula. X bar plus or minus c alpha over 2 times sigma over root m. That's a 100 times 1 minus alpha % confidence interval for mu,
when sigma is known.
Spelled out as a band. Mu sits between x bar minus that margin and x bar plus that margin. Estimate in the middle, margin on each side. That's the whole machine.
Let's pin down that z alpha over 2, because it's doing a lot of work.
It's a cutoff on the standard normal. We pick it so the area between minus it and plus it is 1 minus alpha, our confidence level. Look at the bell. The shaded middle is the confidence, and the two gold tails each carry area alpha over 2.
So the leftover alpha gets split evenly between the two tails. That's the over 2.
Exactly. And notice the trade-off. If you want more confidence, alpha shrinks. The cutoff z alpha over 2 grows, and the interval gets wider. More certainty costs you precision.
And the 3 you'll use constantly are right there in the table. 90% gives 1.645, 95% gives 1.96, and 99% gives 2.575. Worth memorizing the middle one at least.
Where did those numbers come from? The standard normal table, table A3.
And the one trap to remember, the table gives phi of z, the area to the left of z, but z alpha over 2 is defined by the area to its right.
So you do one flip. Area alpha over 2 to the right means 1 minus alpha over 2 to the left. For 95%, that's 0.975. For 90%, 0.95. For 99, 0.995. Those are the numbers you hunt for in the body of the table.
And the excerpt shows it. Find 0.975 and it sits exactly at z equals 1.96. 0.95 falls between two cells, giving 1.645, and 0.995 lands you at 2.575. Read the body, report the edge. Let's actually do one. Zinc concentration in a river. They sample 36 locations. The average comes out to 2.6 grams per milliliter, and we happen to know the population sigma is 0.3.
First, the standard error, sigma over root m. That's 0.3 over root 36, which is 0.3 over 6 equals 0.05. That's our building block.
Now 95%. Z is 1.96, so the margin is 1.96 times 0.05, about 0.098. 2.6 plus or minus that gives roughly 2.50 to 2.70.
Push it to 99%, and Z jumps to 2.575. Same data, same standard error, but the margin grows to about 0.13, so the interval stretches to 2.47 up to 2.73. You can see it on the right. Demanding more confidence just widens the bracket.
That half-width has a name worth knowing, the margin of error, E, z alpha over 2 times sigma over root m. The picture up top makes it concrete. Your estimate, x bar, sits a little off from the true mu, and that small gap is the error, and it can't be bigger than one margin E, the reach from the center out to each edge of the interval.
And it comes with a guarantee. That's the nice part.
Right. With 100 times 1 minus alpha % confidence, the error, the distance between x bar and the true mu, won't exceed E. The margin is a promise about how wrong you could be.
So what makes the margin big or small? 3 dials. It widens if you demand more confidence, or if the data are more spread out, bigger sigma. It shrinks as a sample grows, but only through root m, so you fight diminishing returns. 4 times the data to have the margin.
And to close the loop, for the zinc data, that 95% margin was 0.098. That is the plus or minus in 2.6 plus or minus 0.098. Same object, start to finish.
Here's a question a planner actually asks. I haven't collected data yet, but I want my margin small enough. How many measurements do I need?
Run the margin formula backward. You want z alpha over 2 times sigma over root m to be less than your target error, little e. Solve that for m and you get m is bigger than z alpha over 2 times sigma over e, all squared. And always round up because a fraction of a measurement isn't a measurement.
Let's size the zinc study. Say we want 95% confidence with the error under 0.05. So that's 1.96 times 0.3 over 0.05 squared. The inside is 11.76, and squaring gives about 138.3.
Round up and you need 139 locations. Notice the logic flipped. Instead of reporting a margin after the fact, you designed the study to hit one in advance.
One more variation.
Sometimes you don't care about both directions. You only want an upper limit or only a lower one. A safety ceiling, say.
So how does that change things?
You stop splitting alpha. Instead of alpha over 2 in each tail, you dump the whole alpha into one tail and use Z alpha. Look at the picture, a single gold tail of area alpha and one cutoff. Upper bound, mu is below x bar plus Z alpha times sigma over root m. Lower bound flips the sign.
And one thing that surprises people, a 95% one-sided bound uses Z 0.05, which is 1.645, not the 1.96 from the two-sided interval. Because all of alpha is in the single tail, the cutoff is actually smaller.
Quick example, reaction times, 25 subjects, average 6.2 seconds, sigma is 2. The upper 95% bound is 6.2 plus 1.645 times 2 over root 25. That's 6.2 plus 0.658. So we're 95% confident the true mean is below 6.86 seconds.
Now let's level up. Often the real question isn't what is mu, it's do two groups actually differ? Treatment versus control, before versus after.
And the estimate is exactly what you'd guess. Take the two sample means and subtract. X bar 1 minus X bar 2 estimates the true difference, mu 1 minus mu 2.
And does the Central Limit Theorem still ride to the rescue?
It does. The difference is again approximately normal, and now the standard error combines both samples. Root of sigma 1 squared over m1 plus sigma 2 squared over m2. Two sources of wobble added under the root.
So the interval has the very same shape as the one sample case? The difference x bar 1 minus x bar 2 plus or minus Z alpha over 2 times that combined standard error. Estimate in the middle, margin on each side. We just changed what the estimate and the standard error are.
Let's run one. A treatment is supposed to cut how much metal a bath strips off a part. Untreated, 100 pieces, average 12.2 millimeters removed, sample SD 1.1. Treated, 200 pieces, average 9.1, sample SD 0.9.
Both samples are big, so we let S stand in for sigma. The difference is 12.2 minus 9.1, which is 3.1. For 98% confidence, Z is 2.33. Margin is 2.33 times the combined standard error, and that works out to about 0.3. So the interval is 2.80 to 3.40.
And here's the punchline, the move you'll use again and again. The whole interval sits above 0. 0 is nowhere inside it. So with 98% confidence, the difference is genuinely positive. The treatment really does reduce the metal removed. If 0 had landed inside the interval, we couldn't have claimed any real difference at all.
Quick practical note before we wrap. If you don't want to hunt through a table, GeoGebra's free probability calculator hands you these critical values directly. Choose the normal, 0, 1, set the central probability to 0.95, and it shades the middle and reads off the cutoffs at plus and minus 1.96, the very Z 0.025 we looked up. Bump the central area to 0.99, and the cutoffs widen to plus and minus 2.575. Same answers, no table.
Let's gather it up. Today, we built the confidence interval for a mean, x bar plus or minus Z alpha over 2 times sigma over root m, when sigma is known.
Plus the margin of error and its guarantee, choosing a sample size in advance, one-sided bounds, and even comparing two groups with a difference of means. But there's a catch sitting in that formula, isn't there?
There is. Every interval today assumed we know sigma, the population spread. And in real data, we almost never do.
So next time, lecture 15, we estimate sigma from the sample itself with S. That swaps the normal for week 3's t-distribution, the t-interval, and we'll do the same thing for a proportion, like that poll we opened with. See you there.